Welcome to 5.7 inverse trig integration. So our first theorem that we're going to look at is just all the integrals involving inverse trig functions. So you just have to know these guys, all right? So our goal is to rewrite our integrals in terms of these functions here so that we can integrate it for those inverse trig functions. So if u is differentiable function of x and a is greater than 0, where a is a constant, then the integral of du over the square root of a squared minus u squared is really the arc sine of u over a plus c. All right? If we have the integral of du over a squared plus u squared, it's equal to 1 over a arctangent of u over a plus c. And then we have the integral of du over u times the square root of u squared minus a squared. That's equal to 1 over a times the arcsecant of the absolute value of u over a plus c. Again, know these, write them down, helps you memorize them. Now we're going to get into some examples, different methods for evaluating these integrals. All right, and again, our goal is to rewrite what we currently have for our integrals so that they look like they are in one of these three forms so that we can integrate it. So this first example here, we are integrating dx over 12 plus x plus 3 squared. So this kind of looks like part 2 up here where we're dealing with arctangent. So if we do a u substitution and let u be x plus 3, because that's our variable, all right, then du, taking the derivative of that, is simply just dx. If we let a squared be 12, then a is simply the square root of 12, which we could simplify even further if we wanted to be 2 root 3. Okay, all right, so now when we make that substitution, it works out nicely. We're taking the integral of du over a squared plus u squared, and we should recognize that, hey, that is the integral for arctangent. So when we go through, we integrate it. It's 1 over a times arctangent of u over a plus c. Now we just substitute back. So a is the square root of 12 times the arctangent, so 1 over square root of 12 times the arctangent of our u, which is x plus 3, over root 12 plus 3. Now just rewriting and rationalizing the denominator here. We clean it up to be root 3 over 6 times the arctangent of root 3 times x plus 3 all over 6 plus c. I'm totally fine if you left your answer like this up above that first line, but just recognize that you might see it rationalized later on. This next example, if we are thinking a u substitution and we let u be the denominator, we would still be left with a variable, with a function that has that x variable, and it wouldn't work out. So what can we do? Well, if we complete the square for this quadratic, it'll allow us to put it in the form for integrating with arctangent. So let's complete the square. So what I did right away is I threw that constant 13 way off to the side, and I created 2 blanks. All right, so remember, we take this middle term, we divide by 2, and we square it. So this portion is the completing the square. However, since I added 9 to keep everything balanced, we need to subtract 9. So we factor this portion here, and that becomes our x minus 3 squared. We clean up this negative 9 plus 13 to get 4. So now it's in that form of a squared plus u squared. So I rewrote that integral, the integral of dx over 4 plus x minus 3 squared, and now it becomes an example just like up above where we have a u is x minus 3, du is simply dx. We let a squared be 4, so a is 2, and we can rewrite it as the integral of du over a squared plus u squared, which integrates as 1 over a times the arctangent of u over a plus c, and now all we have to do is substitute back for our final answer. This next example is a bit more complicated because we have multiple terms in our numerator okay, that we're adding together, and we have a product of functions in the denominator. So what we can do is we can rewrite this numerator so it's a sum of two quotients. So we're just going to break up that numerator. So we have the integral of x to the fourth over the denominator, dx, plus the integral of the other portion of our numerator, 4 over x times the square root of x to the fourth minus 4 dx. And now, when we simplify x to the fourth over x, we're going to be left with x cubed in the numerator. So this first integral becomes a nice u substitution where we let u be x to the fourth minus 4, and then du is going to be 4x cubed dx. So that takes care of the x cubed dx portion, and don't forget to pull out the 1/4 in front. So what we're really integrating is 1/4 times the integral of du over the square root of u. Now shifting focus over to the right side. We can pull this 4 out front, and now we have to think about, well, what can we make this portion potentially look like? And if you look up above, the arcsecant is where we have a variable times the square root of another function. So our goal is going to get it to look like that. So as we go through, if we let u be x squared, then du is 2x dx, all right? Or simply, we can pull that 1/2 out, okay? A squared would be the 4, so a is 2. Now, in order for us to get it to look like the integral for that arcsecant, what we need to do is we need to have an x over an x squared. And this isn't changing the 1 over x value, but it allows us to then rewrite this x squared as the u, and then this du portion is taken care of in this aspect here. Right there, okay? And so now when we go ahead and we are ready to make that kind of u substitution, because of du is 2x dx, we really have 1/2 du equals x dx. So we're going to pull that 1/2 out, and now we're going to make our substitutions. So remember, u is x squared, so that's this piece right here. Then underneath that radical, we have u squared minus a squared. So this is where our arcsecant comes into play. So just cleaning everything up now, we have 4 times 1/2 is where we get the 2 from. Integrating this, we have 1 over a times the arcsecant of the absolute value of u over a plus c. Going back to the orange aspect over here, we can integrate 1 over the square root of u, and that's going to be 2 times u to the 1/2. And now we just substitute back in for the orange. We make our substitutions for the a and the u for our purple. And now the last thing we're going to do is just clean up this final aspect here. I can drop the absolute values because x squared is always going to be positive. 2 times 1/2, that goes away, and we are left with our final answer here. Our next example deals with related rates. On a morning of a day when the sun will pass directly overhead, an 80-foot building on level ground is casting a shadow onto the ground. At the moment in question, the length of the shadow is decreasing by 2 feet per minute. So that's key. Find the rate of the angle between the ground and the sun is changing when the shadow is 60 feet long. So I always start related rates off with what we know versus what we want. Okay, so we know that the length of the shadow, which I called x, all right? So if we draw our picture, theta is that angle with the ground. Our 80-foot building is casting the shadow. So our sun, if we're getting creative, is over here. Okay, casting that shadow of the building. Again, x is the shadow. So we know that the rate of the shadow is decreasing by 2 feet per minute. So dx dt is -2 feet per minute. what do we want? Well, we want the rate of the angle, what that changes, right? So that's d theta dt. And we want that when the shadow is 60 feet long. So this is what we want with that information. So we don't use that until the very, very end. All right. So as we go back to kind of what we know and using that, since we have our triangle here, we can set up tangent of theta equals 80 over x, but we want our equation in terms of theta because in the end we want d theta dt. So theta in terms of x is equal to the arctangent of 80 over x. So now to find what d theta dx is, remind yourself that the derivative of the inverse tangent or arctangent of u is u prime. So the derivative of that value inside over 1 plus u squared. Okay, so if u is 80 times x to the negative 1, u prime is going to be negative 80 x to the negative 2. And so we go through and we can say d theta dx is that u prime, which is negative 80 over x squared, over 1 plus u squared. And when we simplify everything, what we can do to make it a little nicer so we don't have all these fractions within fractions, I'm going to multiply the numerator and the denominator by x squared. Okay. And when we do that, it cleans up nicely. So d theta dx is equal to negative 80 over x squared plus 80 squared. So we can leave it in terms of that. And now that's going to help us find what we want. So we eventually need to talk about d theta dt. So how do we get to d theta dt when we only have d theta dx? So d theta dt is equal to d theta dx times dx dt. The dx's would cancel and we'd be left with d theta dt. So now we just make our substitution. We know d theta dx. We found that over here. So we make that substitution. We also know dx dt, the rate at which the shadow is changing, is negative 2 feet per minute. So we make that substitution. And we want to evaluate this when x, the length of our shadow, is 60 feet. So now we just make that substitution and we clean everything up. And we get 2 over 125 radians per minute. If we were to throw that onto the calculator, we would really get 0.016 radians per minute. This last example we're actually going to do together in class next time we see each other. However, if you want to try it on your own and then kind of check back, feel free to do so. I'll leave it up here so you can kind of copy it down if you'd like to give it a try or just to come back and check. Otherwise, again, we'll go through this in class together. If you have questions on anything else, make sure you let me know.